We are live. We are live. Welcome, everybody. So this is the first stream of Introduction to Networking. I had a little bit of break from streaming Python since the last stream was 2 weeks ago, I believe, and it was a disaster. It was kind of a disaster. But it's something that we expect. It's not everything goes smoothly. But what's important that I didn't completely, of course, stop learning Python. I did during my days, and I did some progress. But now we need to focus on networking a little bit. This is something, in general, you have to realize which are the things you should focus on, which are benefiting you at the present moment. And also, if we are going into the world of technology, right, like this is our goal, this is our task, then basically anything technology related should be something which we are like, it's in our sensor, and it's our end goal, and we are going all in. That, okay, so I'm gonna learn as much as I can about this topic, because that's what it's all about. There's always something new, and then you have to like go all in. And the idea is that we know what we need right now. This is also very critical because we should be aware. So yeah, in any case, this will be very interesting. I did read it actually a little bit about it, because right, like we went through, I think, Python 12 or 13, like the network web applications. And it actually naturally recommended you, like, this is Dr. Chuck's book, which we're gonna go through. So, do you see it? Yeah, see? And now, so I made very nice adjustments to the stream. I cannot believe how easy it was. Like the black bars, I managed to remove the black bars. See? There are no black bars. And all it was, just hold the Alt. So I cannot believe I was streaming for 13 weeks without figuring this out, or without even trying. Anyway, and also, yeah, the book now is, I think it's much more nicely. You can also see what I see. And yeah, this stream, I believe, it's really, I don't think there will be any programming like in VS Code. Who knows, maybe later. But my idea is that I read it, and I rewrite it in my own sentence, and we try to imagine how it actually, like, that in order for us to make sense for us. Like, yeah, day before yesterday I started about this, and I know carrier sense multiple access with collision detection. This is burned into my brain, and this means is that when two computers sending packets, there's a carrier sense that it's like listening if there is anything incoming. If there's silence, I'm gonna send my packet. If there's collision detection, then both of them will stop for a different length of time, so that they can let the other one send the packet, basically. And this is the link layer. I have a link layer here in my hand. Oh, okay. Yes, and yeah, ADHD. Regarding ADHD, we had our ups and downs, but now 11:30. Yeah, I think I will just try to be clear in this stream. I try to be really clear about the medication and how, not to, because it should be a reference point for someone who is also wanna study with ADHD, or they are on the medication or whatever. So I'm gonna be clear about what is the dose, when I'm gonna take it. So today I had very nice breakfast, oatmeal, banana, not overly. That don't overeat, guys. This is big enemy of our life, of overeating. So just normal amount of food. It's still digesting, but yeah, at 11:30 I will take 10 milligrams of Ritalin, and then we should be good until like, yeah, 4-ish. So yeah, there is already a little bit of delay with the lunch and everything, but yeah, I want to do today at least good 4 hours. Good 4 hours should be done. Yeah, and generally just interest. This is very interesting topic. like literally interesting, because we are using this technology every day and we have absolutely no idea what's going on. And now, you know, we're gonna have at least some idea, or we can name things. We're not gonna ever understand it in engineering level and creating, but we're gonna be able to have a conversation about it, and I think that's pretty fucking cool. So okay, so with this intro, let's get started, and yeah. So let's do some little background, because this is where I stopped day before yesterday, but let's go back into my notes a little bit, because, or we can even read, yeah, the first one. To engineer and build a system as complex as the internet, engineers try to break a single challenging problem into a set of smaller problems that can be solved independently and then put back together to solve the original large problem. Let me read it from the book. Why would you do this? Yeah, let's read a little bit of introduction. So using the internet seems pretty easy. Yeah, I have to, of course, add this book is written by Dr. Chuck. I really like his teaching style. It's really, I never had online mentor or anybody like who I would really follow so consistently and for so long. So this speaks volumes of Dr. Chuck's teaching method, and it's very nice to see that he's still active. Like I saw an interview about commenting on AI and everything. So I hope, Dr. Chuck, if you see this, please come to Prague, and I need to get a signature. I need to, of course, physically get your book, but yeah, that would be super cool. Anyway, using the internet seems pretty easy. We go to a web address and up comes a page. Or we go to our favorite social site and see pictures of our friends, families, and pets. But it takes a lot of complex software and hardware to make the internet seem so simple. The design of these technologies that make today's internet work started in the 60s, and there were over 20 years of research into how to build internet working technologies before the first internet was built in the late 80s by academics in the project called NSFNet. Since then, the research and development into improving network technologies has continued as networks have become far larger and faster and globally distributed with billions of computers. In order to better understand how today's internet works, we will take a look at how humans and computers have communicated using technology over the years. So I remember reading this. We were on the train, we were going to Klitsch, and on the way back I started to read this. And it's fun, yeah. I mean, it's interesting, but this is really go to prehistoric way of detailing into. So I'm not sure if I wanna go through all of this, to be honest. Okay, it's not that long. Let's read the history. It's gonna get our brain at least into a little bit of. Let's read the introduction. Communicating at a distance. Imagine a group of 5 people in a room sitting in a circle. As long as they are corteos.
Courteous and don't have more than one conversation at the same time, it's quite natural for any person to talk to.
Cortus. Okay, one second. I will be right back. I really need to understand how this works now. Yeah, I'm gonna do it in another window. Oof. Okay, this is perfect.
Courteous.
Courteous, that's the word, courteous. Courteous. As long as they are courteous and don't have more than one conversation at the same time, it's quite natural for any person to talk to any other person in the room. They just need to be able to hear each other and coordinate how to use shared space in the room. But what if we put these people in different rooms so they can no longer see or hear each other? How could pairs of people communicate with each other then? One way might be to run a wire between each pair of people with a microphone on one end and a speaker on the other end. Now everyone could still hear all the conversations. They would still need to be courteous to make sure that there was only one conversation going on at the same time. Each person would need 4 speakers, one for each of the other people, and enough pieces of wire to connect all the microphones and speakers. This is a problem with 5 people, and it gets far worse when there are hundreds or thousands of people. Using wires, microphones, and speakers is how early telephone systems from the 1900s allowed people to make phone calls. Because they could not separate wires between every pair of telephones, these systems did not allow all pairs of people to be connected at the same time. Each person had a single connection to a human operator. The operator would connect 2 wires together to allow a pair of people to talk, and then disconnect them when the conversation was finished. The first local telephone systems worked well when a customer's home or business was close to the operator's building and a wire could be strung directly from the operator's building to the person's home. You can see long distance telephone phones, and it's actually funny because I didn't notice, but I don't really actually see them anymore. And it was such a they disappeared, or I just stopped paying attention to them. But anyway, but what if thousands of people who are hundreds of kilometers apart need to be able to communicate? We can't run 100-kilometer wires from each home to a single central office. What the telephone companies did, excuse me, what the telephone companies did instead was to have many central offices and run a few wires between the central offices and then share connections between central offices. For long distances, a connection might run through a number of central offices. Before the advent of fiber optic, long-distance phone calls were carried between cities and on poles with lots of separate wires. The number of wires on the poles represented the number of possible simultaneous long-distance phone calls that could use those wires. Since the cost of the wires went up as the length of the wire increased, these longer connections between offices were quite expensive to install and maintain, and they were scarce. So in the early days of telephones, local calls were generally quite inexpensive. But long-distance calls were more expensive and they were charged by the minute. This made sense because each minute you talked on a long-distance call, your use of the long-distance wires meant no one else could use them. The telephone companies wanted you to keep your calls short so their long-distance lines would be available for other customers. When telephone companies started using fiber optic, more advanced techniques were used to carry many simultaneous long-distance conversations on a single fiber. When you look at an old photo and see lots of wires on a single pole, It generally means that they were telephone wires and not used to carry electricity. Computers communicate differently. When humans talk on the phone, they make a call, talk for a while, and then hang up. Statistically, most of the time, humans are not talking on the phone. At least they weren't before everyone had smartphones. But computers, including applications on your smartphone, communicate differently than humans do. Sometimes computers send short messages to check if another computer is available. Computers sometimes send medium-sized information like a single picture or a long email message. And sometimes computers send a lot of information like a whole movie or a piece of software to install that might take minutes or even hours to download. So messages between computers can be short, medium, or long. In the earliest days of connecting computers to another, pairs of computers were connected with wires. The simplest way to send data from one computer to another was to line up the outgoing messages in a queue and send the messages one after another as fast as the computers and the wires could carry the data. Each message would wait for its turn until the messages ahead of it were sent, and then it would get its chance to be sent across connection. When the computers were in the same building, the building owner could run wires to connect them. If the computers were in the same town, the owners of the computers generally had to lease wires from the telephone companies to connect their computers. They often would have the phone company connect the wires together in their central office so that it was not necessary for one computer to dial the other computer to send data. These leased lines were convenient for computer communications because they were always on, but they were also quite expensive because they were also used 24 hours a day. When the computers were even farther away in different cities, the leased lines were extended using the longer wires connecting the central offices. Since there were so few wires between central offices, these long-distance leased lines were quite expensive and their cost increased dramatically as the length of the leased line increased. But if you had enough money, you could lease direct connections between your computers so they could exchange data. This worked pretty well as long as you were only using one brand of computers, because each computer company had their own way of using telephone wires to connect their computers together and send data. Ooh, sounds so awkward. Early wide area store and forward networks. In the 1970s and 80s, people working at universities around the world wanted to send other data and messages using these computer-to-computer connections. Oh, this is my time. In the 1970s and 80s, people working at universities around the world wanted to send each other data and messages using these computer-to-computer connections. Since the cost for each connection was so high and increased with distance, computers generally only had connections to other nearby computers. But if the computer that you were connected to was connected to another computer, and that computer in turn was connected to another computer, and so on, you could send a message a long distance as long as each of the computers along the route of the message agreed to store and forward your message. Over time, with relatively few connections, you could send data long distances across a patchwork of network connections as long as you were patient. Along the way, after your message reached one computer, it would have to wait until its turn came to be Along the way after your message reached one computer, it would have to wait until its turn came to be sent. What? Along the way after your message reached one computer, it would have to wait until its turn came to be sent to the next computer along the route. A message would arrive at the intermediate computer, be stored for a while, perhaps hours, depending on traffic, and then forwarded one more connection, or hop. Yeah, we're gonna talk about hops. Sending entire messages one at a time this way, a message might take minutes, hours, or even days to arrive at its ultimate destination, depending on the traffic at each of the hops. But even if it took a few hours for an email message to find its way from one part of the country to another, this was still much quicker and easier than sending a letter or postcard. Packets and routers. The most important innovation that allowed messages to move more quickly across a multi-hop network was to break each message into a small fragments and send each fragment individually. In networking terms, these pieces of messages are called packets. The idea of breaking a message into packets was pioneered in the 60s, but it was not widely used until the 80s because it required more computing power and more sophisticated networking software. When messages are broken into packets and each packet is sent separately, if a short message was sent after a large message had begun, the short message did not have to wait until the entire long message was finished. The first packet of a short message only had to wait for the current packet of the large message to be finished. The system alternated sending packets from the long and short messages until after a while the short message was completely sent and the long message resumed making full use of the network connection. Breaking the message into packets also greatly reduced the amount of storage needed in the intermediate computers because instead of needing us to store an entire message for as long as a few hours, the intermediate computer only needed to store a few packets for a few seconds while the packets waited for their turns on the outbound link. As network moved away from store and forward approach, they started to include special purpose computers that specialized in moving packets. These were initially called interface message processors, IMPs, because they acted as the interface between general purpose computers and the rest of the network. Later, these computers dedicated to communications were called routers because their purpose was to route the packets they received towards their ultimate destination. By building routers that specialized in moving packets across multiple hops, it became simpler to connect computers from multiple vendors to the same network. By building routers that specialized in moving packets across multiple hops, it became simpler to connect computers from multiple vendors to the same network. To connect any computer to the network, now all you needed to do was connect it to one router, and then the rest of the communication details were handled by other routers. When multiple computers at one location were connected together in a local area network, using physical wiring, you would connect a router to the local area network. By sending data through the router, all the computers on the local area network would send across the wide area network, or WAN. So these are again like important terms because this is something we already use, right? Oh my god. Ooh. Oh shit. In the early store and forward networks, it was important to know the source and destination computers for every message. Each computer was given a unique name or number that was called the address of the computer. To send a message to another computer, you needed to add the source and destination address to the message before sending the message along its way. By having a source and destination address in each message, the computers that stored and forwarded the message would be able to pick the best path for the message if more than one path was available. When a long message was split into much smaller packets and each packet was sent individually, the source and destination addresses had to be added to each packet so that routers could choose the best path to forward each packet of the message. In addition to the source and destination addresses, it was also necessary to add data to each packet indicating the offset or position of the packet in the overall message so that the receiving computer could put the packets back together in the right order to reconstruct the original message. Putting it all together. So when we combine all this together, we can understand the basic operations of today's internet. We have specialized computers called routers that know how to handle route packets along a path from a source to the destination. Each packet will pass through multiple routers during its journey from the source computer to the destination computer. Even though the packets may be part of a larger message, the routers forward each packet separately based on its source and the destination addresses. Different packets from the same message may take different routes from the source to the destination, and sometimes packets even arrive out of order. A later packet might arrive before an earlier packet, perhaps because of a data traffic jam. Each packet contains an offset from the beginning of the message so that the destination computer can reassemble the packets in the correct order to reconstruct the original message. By creating a network using multiple short hops, the overall cost of communicating across a large geographical area could be spread across a large number of connecting groups and individuals. Normally, packets would find the shortest path between the source and destination, but if a link on the path was overloaded or broken, the routers could cooperate and reroute traffic to take slightly longer path that would get packets from a source to a destination as quickly as possible. The core of the internet is a set of cooperating routers that move packets from many sources to many destinations at the same time. Each computer or local area network is connected to a router that forwards the traffic from its location to the various destinations on the internet. A router might handle data from a single computer, like a smartphone, from several computers in the same building, or from thousands of computers connected to a university campus network. The term internet comes from the idea of internetworking, which captures the idea of connecting many networks together. Our computers connect to the local networks, and the internet connects to the local network together, so all of our computers can talk to each other. Okay, let's do the quiz. How does the quiz look like if I open it here? You guys don't see it, right? Yeah. I will put it here. Yeah, that's a good idea. What did the early telephone operators do? That's right. What is a leased line? Boundary of the connection, a wire that runs from one company to another. Boundary between leased and owned telephone. A connection between keyboard, a wire that runs from one phone company office to another. I guess. How long might a message be stored in an intermediate computer for store for the network? I have no idea. What is a packet? The amount of data? No. A portion of larger message sent across the network. Which of these most like a router? Mail sorting facility. What was the name given to early network routers? I would say interface message processors. In addition to breaking large messages into smaller segments to be sent, what else was needed to properly route each message segment? Because so many people share all the resources, I guess. Okay, so these are correct. Okay, so how long? A wire for then from, okay, so boundary between leased and owned telephone equipment. So an always on network telephone connection, and how long? All right, let's move on. All right, so I read the intro. That's it. This is something which is I already read, right? I already read at work, and yeah, I will try to this part. Let me just go through my notes, basically, because what do we know here? This is like the let me try to tell you from my head, from what I know from here, so that in order for the internet to work, there are 4 engineering layers. The engineers came up with 4 layers which all use each other in order to make this thing work, which is there's link layer, internetwork layer, transport layer, and application layer. Yeah, I will go through it. It's okay. So, to engineer and build a system as complex as the internet, engineers try to break a single challenging problem into a set of smaller problems that can be solved independently and then put back together to solve the original large problem. The engineers who built the first internets broke the overall problem into 4 basic subproblems that could be worked on independently by different groups. They gave these 4 areas of engineering the following names: link, internetwork, transport, and application. We visualize these different areas as layers stacked on top of each other, with the link layer on the bottom and the application layer on the top. The link layer deals with the wired and wireless connection from your computer to the local area network, and the application layer is what we as end users interact with. A web browser is one example of an application in this internet architecture. We informally refer to this model as the TCP/IP model in reference to the transport control protocol used to implement the transport layer and an internet protocol used to implement the internet layer. Okay. So this is good because TCP/IP. What is TCP/IP stands for? This is definitely some question which they could ask you. So this whole model refers these 4 layers. TCP/IP model means transfer control protocol used to implement the transport layer. TCP. The TCP is used to implement the IP. Transport control protocol used to implement the transport layer, and internet protocol, which is used to implement the internetwork layer. So that's the whole point of this book, is to get used to this, like to really be able to talk about these things. TCP/IP, transfer control protocol, which is used to implement the transport layer, and Internet protocol, which is used to implement the internet network layer, obviously. Whatever this means, guys, whatever this means. The link layer is responsible for connecting your computer to its local network and moving data across a single hop. The most common link layer technology today is wireless networking. When you are using a wireless device, the device is only sending data a limited distance. A smartphone communicates with a tower that is a few kilometers away. If you are using your smartphone on a train, it needs to switch to a new tower every few minutes when the train is moving. A laptop that is connected to a Wi-Fi network is usually communicating with a base station within 200 meters. Desktop computer that is connected using a wired connection is usually using a cable that is 100 meters long or shorter. Link layer technologies are often shared amongst multiple computers at the same location. The link layer needs to solve two basic problems when dealing with these shared local area networks. The first problem is how to encode and send data across the link. If the link is wireless, engineers must agree on which radio frequencies are to be used to transmit data and how digital data is to be encoded in the radio signal. For wired connections, they must agree on what voltage to use on the wire and how fast to send those bits across the wire. For link layer technologies that use fiber optics, they must agree on the frequencies of light to be used and how fast to send the data. In addition to agreeing on how to send data using a shared medium such as a wireless network, they also need to agree on how to cooperate with other computers that might want to send data at the same time. If all the computers on the network try to transmit whatever they had data to send, their messages would collide. The result would be chaos, and receiving stations will receive only noise. So we need to find a fair way to allow each station to wait its turn to use the shared network. The idea of breaking a large message into packets and then sending each packet separately makes this sharing easier. If only one computer wants to send data, it will send its packets one right after another and move its data across the network as quickly as it can. But if three computers want to send data at the same time, each computer will send one packet and then wait while the other two computers send packets. After each of the other computers send a packet, the first computer will send its next packet. This way, the computers are sharing access to the network in a fair way. But how does a computer know if other computers want to send data at the same time? Engineers designed an ingenious method to solve this problem called Carrier Sensed Multiple Access with Collision Detection, or CSMA/CD. It is a long name for a simple and elegant concept. When your computer wants to send data, it first listens to see if another computer is already sending data on the network. Carrier sensed. If no other computer is sending data, your computer starts sending its data. As your computer is sending data, it also listens to see if it can receive its own data. If your computer receives its own data, it knows the channel is still clear and continues transmitting. Yeah. If it can. But if two computers started sending at about the same time and data collides, and your computer does not receive its own data, when a collision is detected, both computers stop transmitting. Wait a bit and retry the transmission. The two computers that collided wait different lengths of time to retry their transmissions to reduce the chances of second collision. When your computer finishes sending a packet of data, it pauses to give other computers that have been waiting a chance to send on data. If another computer senses that your computer has stopped sending data, and starts sending its own packet, your computer will detect the other computer's use of the network and wait until the computer's packet is complete before attempting to send its next packet. This simple mechanism works well when only one computer wants to send data. It also works well when many computers want to send data at the same time. When only one computer is sending data, that computer can make good use of the shared network by sending packets one after another. And when many computers want to use this shared network at the same time, each computer gets a fair share of the link. Okay, break time. I have to find a good break song or something.
Courteous. Courteous.
Okay. So I figured out that this Pomodoro technique, which people were talking about, is it called Pomodoro or Pomodoro? Is 25 minutes, Markov, then enjoy 5-minute break. After 4 pound, take longer, more, restore 30 minutes break. Great. So that, because when I was doing the programming, like the Visual Studio, and when you're really trying to focus on one thing, it's very hard to, this doesn't work at all, because I cannot just take a break when I'm trying to solve a problem, because I need to keep thinking about it. And if I take a break, maybe I will go too far from the solution. So it didn't work. But with reading new information, reading and documenting new information, it could work. So I'm gonna set another timer for 25 minutes. So we're gonna try the Pomodoro here. So some link layers, like a cellular connection for a smartphone or a Wi-Fi connection or a satellite or cable modem, are shared connection and need techniques like carrier sense, multiple access with carrier detection or with collision detection to ensure fair access to the many different computers connected to the network. Other link layers like fiber optic cables and leased lines are generally not shared and are used for connections between routers. These non-shared connections are still part of the link layer. The engineers working on the link layer technologies focus solving the issues so computers can transmit data across a single link that ranges in distance from a few meters to as long as hundreds of kilometers. But to move data greater distances, we need to send our packets through multiple routers connected by multiple link layers. Each time our packet passes through another link layer from one router to another, we call it a hop. To send data halfway around the world, it will pass through about 20 routers or make 20 hops. The internetwork layer, IP. So the IP means here that the internet protocol is responsible for the internetwork layer. And here, link layer, we don't have anything next to it. So that's very interesting, by the way, because see, again, TCP. So this is what it means. Transfer control protocol, right? No, transport. It's the same word, same rate. So you don't even have to like. Transport control protocol is responsible for the transport layer, and the internet protocol is responsible for the internetwork layer. Once your packet distant for the internet makes it across the first link, it will be in a router. Your packet has a source address and destination address, and the router needs to look at the destination address to figure out how to best move your packet towards its destination. With each router handling packets destined for any of many billions of destination computers, it's not possible for every router to know the exact location and best route to every possible destination computer. So the router makes its best guess as to how to get your packet closer to its destination. Each of the other routers along the way also does its best to get your packet closer to the destination computer. As long as your packet gets closer to the final destination, the routers have a better idea of where your packet needs to go. When the packet reaches the last link in its journey, the link layer knows exactly where to send your packet. We use a similar approach to route ourselves when, okay, I really didn't like this like reference. Focus, please, I'm begging you. We use a similar approach to route ourselves when going on a holiday. A holiday trip also has many hops. Perhaps the first hop is driving your car or taking a cab or bus to a train station. then your local train from your small town to a larger city. In the larger city, you take a long distance train to a larger city in another country. Then you take another local train to the small village where you will stay for your holiday. When you get off the train, you take a bus. When you get off the bus, you walk to your hotel. If you were on the train between two large cities and you ask the conductor to exact location of your hotel in a small village, the conductor would not know. He would be like, what the fuck are you asking me about? The conductor only knows how to get you closer to your destination, and while you're on the long distance train, that is all that matters. When you get on the bus at your destination village, you can ask the bus driver which stop is closest to your motel. And when you get off the bus at the right bus stop, you can probably ask a person on the street where to find a hotel and get an exact answer. The further you are from your destination, the less you need to know and the exact details of how to get there. When you are far away, all you need to know is how to get closer to your destination. Routers on the internet network work the same way. Only the routers that are closest to the destination computer know the exact path to the computer. All of the routers in the middle of the journey work to get your message closer to its destination. But just like when you're traveling, unexpected problems or delays can come up that require a change in plans as your packets are sent across the network. Routers exchange special messages to inform each other about any kind of active traffic delay or network outage so that packets can be switched from a route that is no longer working to a different route. The routers that make up the core of the internet are small and adapt quickly to both small and large outages or failures of network connections. Sometimes a connection slows down because it is overloaded. Other times a connection is physically broken when the construction crew mistakenly digs up a buried wire and cuts it. Sometimes there's a net, and by the way, I'm just kind of having a side note. I really think that for my position or my situation, the only thing I really have to be really knowing is the application layer and the link layer. Like I have to be really knowing, because if I find out that there is that these two are set, then it can I think this is I suspect it's for me it's application and link layer. I have to make sure if there's a network issue, if both or these are the issue is not lying there. Because transport and inter-network layer is already happening beyond my control, right? I don't know. Sometimes there is a natural disaster like a hurricane or typhoon that shuts down the routers and links in a large geographical area. The routers quickly detect these outages and reroute around them if possible. But sometimes things go wrong and packets are lost. Dealing with lost packets is the reason for the next layer in our architecture. So the transport layer, which is one step below the application layer. The inter-network layer is both simple and complex. It looks at a packet's destination address and finds a path across multiple network hops to deliver the packet to the destination computer. But sometimes these packets get lost or badly delayed. Other times the packets arrive at their destination out of order because a later packet found a quicker path through the network than an earlier packet. Each packet contains the source computer's address and the destination computer's address and an offset where this packet fits relative to the beginning of the message. Knowing the offset of each packet from the beginning of the message and the length of the packet, the destination computer can reconstruct the original message even if the packets were received out of order. As the destination computer reconstructs the message and delivers it to the receiving application, it periodically sends an acknowledgement back to the source computer indicating how much of the message it has received and reconstructed. But if the destination computer finds that parts of the reconstructed message are missing, This probably means that these packets were lost or badly delayed. After waiting a bit, the destination computer sends a request to the source computer to resend the data that seems to be missing. The sending computer must store a copy of the parts of the original message that have been sent until the destination computer acknowledges successful receipt of the packets. Once the source computer receives the acknowledgement of the successful receipt of the portion of the message, it can discard the data that has been acknowledged and send some more data. The amount of data that the source computer sends before waiting for an acknowledgement is called the window size. If the window size is too small, the data transmission is slowed because the source computer is always waiting for acknowledgements. If the source computer sends too much data before waiting for an acknowledgement, it can unintentionally cause traffic problems by overloading routers or long-distance communication lines. This problem is solved by keeping the window size small at the beginning and timing how long it takes to receive the first acknowledgement. If the acknowledgements come back quickly, the source computer slowly increases the window size, and if the acknowledgements come back slowly, the source computer keeps the window size small as not to overload the network. Just like the link layer, a little courtesy on the internet goes a long way towards ensuring good of the shared network infrastructure. This strategy means that when the network has high-speed connections and is lightly loaded, the data will be sent quickly, and if the network is heavily loaded or has slow connections, the data will be slowed down to match the limitations of the network connections between the source and destination computers. The application layer. The link, internetwork, and transport layers work together to quickly and reliably move data between two computers across a shared network of networks. With this capability to move data reliably, the next question is what network application will be built to make use of these network connections. When the first widely used internet came into being in the mid-80s, the first network application allowed users to log in to remote computers, transfer files between computers, send mail between computers, and even do real-time text chats between computers. In the early 1990s, as the internet came to more people and computers' abilities to handle images improved, the World Wide Web application was developed by scientists at the CERN High Energy Physics Facility. The web was focused on reading and editing network hypertext documents with images. Today, the web is the most common network application in use around the world, but all the other older internet applications are still in wide use. Each application is generally broken into two halves. One half of the application is called the server. It runs on the destination computer and waits for incoming network connections. One of the applications is called the server. It runs on the destination computer and waits for the incoming network connection. The other half of the application is called the client that runs on the source computer. When you are browsing the web using software like Firefox, Chrome, or Internet Explorer, you are running a web client application which is making connections to web servers and displaying the pages and documents stored on those web servers. The uniform resource locators, URLs, that your web browser shows in the address bar are the web servers that your client is connecting to retrieve documents for you to read. So this is here, which you don't see, but yeah, it's the URL. When we develop the server half, the client, when we develop the server half and the client half of a network application, we must also define an application protocol that describes how the two halves of the application will exchange messages over the network. The protocols used for each application are quite different and specialized to meet the needs of a particular application. Later, we will explore some of these application layer protocols. 11 minutes until the next break. Yeah, the urge to press the phone is huge. Really, this is the biggest enemy of ours, the urge to press the phone for no reason, for no apparent reason. I really wish to figure this out, because this is such a, okay, this is not net connected to networks or anything, but this is very important, because it wasn't always like this. That, you know, I can really see that this is like huge problem, and it's something which your brain get conditioned to just, you know, really this, you have a certain need to indulge in opening short content or scroll. But and that's the funniest thing, that this is it so much effort and care and so much unthinkable minds work together to create this, literally create this what we are reading about. And then me personally, but I think many others, of course, we are using this technology not to our benefit, really not to our benefit. Like we are feeling shittier. Whereas this is, you know, magic. This is amazing that it's working, and it's crazy. But I do have a need. I do have this urge, and it's something I'm conscious about, and I'm trying to fight. But really, like, we could literally use it. We have the power to really use the internet to, yeah, you can use it communication, but meaningful, really, to get in touch with people we are, you know, actively, you know, meet in real life, etc. But this whole social media thing, like to get a glimpse into people's life, and I'm part of this. I'm literally part of this. I really need to have a session dedicated to social media, like to talk about social media, because maybe, you know, I don't want to be the person who is like not part of it at all, like go offline. But on the other hand, so what is the way? Like if you really can control, it's the problem is it's made in a way that you cannot even limit. Like if you're using it just as a, I have no idea. This is like a can of worms. Phew. But yeah, ideally something in between. You share stuff, you are part, you know, you share some, you know, precious moments, but maybe fixed time. Let's even note this down, because I wanna really talk about this on Monday. We usually show the 4 different layers stacked on top of each other, with the application layer at the top and the link layer at the bottom. The reason we show them this way is because each layer makes use of the layers above and below it to achieve network communications. All 4 layers run in your computer, where you run the client application like a browser, and all 4 layers are also running the destination computer, where the application server is running. You, as the end user, interact with the applications that make up the top layer of the stack, and the bottom layer that represents the Wi-Fi, cellular, wired connection here between your computer and the rest of the internet. The routers that forward your packets from one to another to move your packets towards the destination have no understanding of the transport or applications layers. Routers operate at the internet network layers and link layers. The source of the destination addresses at the internetwork layer are all that is needed for routers to move your packets across series of links, hops, to get them to the destination. The transport and application layers only come into play after the internetwork layer delivers your packets to the destination computer. If you wanted to write your own network application, you would likely only talk to the net transport layer and be completely unconcerned about the internetwork and link layers. They are essential to the function of the transport layer, but as you write your program, you do not need to be aware of any of the lower layer details. The layer network model makes it simpler to write network applications because so many of the complex details of moving data from one computer to another can be ignored. Up next, we will talk about these 4 layers in more detail. So yes, so let's do the questions again. I did them the day before yesterday, but why not? Because I know this. Why do engineers use a model to organize? Because they want to break into a set of smaller problems. What is the top layer used by? Transport control protocol and internet protocol net. Transport control protocol and internet protocol networks. This is the application. You are already helping, by the way. You are basically putting them in the same order. Which of these layers concerns itself getting data across a single physical connection, the link layer? Carrier sense multiple access with condition detection. What is the goal of the internetwork layer? That's the second layer, right? So get packets, yeah. In addition to data source and destination addresses, what else is needed to make sure the messages can be received? Yeah. Be definitely the offset. What is a window size? The sum of the length and width, the maximum size of a single packet. The amount of data computer can send before receiving an acknowledgement. In a typical network client server application, where does the client on your laptop? Universal routing language. Uniform routing language, unified resource. Okay, this is still, I don't know, URL. Uniform resource locator, I guess. Yeah. Yeah, this is, we got this. And it's getting cold, guys. Literally getting cold. But there is heating, so I turned on the heating. I can't believe it's literally 20th of April. It's 20th of April. It's for Weed Smokers Day. Happy 420, everybody. Wow, I remember like 2 years ago, 420 was like super sunny day. But not now. Yeah, I can't believe it's already 20th of April. The year is going like crazy again. Oh. So, it's been 1 hour 20 minutes, and we are basically at the part where I stopped reading. So anything that comes now is gonna be really new. So. How much time is left? 2 minutes. I think we're not gonna get into this now. Let me try to check if I have the Pomodoro. Break time. No idea. I'm gonna. Okay, that's it. That was very short break. That was very short break. I didn't even realize. Yeah, so let's try to set up the focus session, right? So how long we want to do it? Daily program. This is so weird. Overdraft. Počka po ruce. Can I delete these? You can even add there. So what is the focus of this chapter? Chapter 3. $50. But if I do it like this, we have one break. Let's try. It says actually I should do for 20 minutes and then 5 minutes of break. I can't believe I'm stuck on thinking about this actually. Okay. Everything is on, still on. Everything is still on. The lowest layer of our internet architecture is the link layer. We call it the lowest layer because it is the closest to the physical network media. Often, the link layer transmits data using a wire, a fiber optic cable, or a radio signal. A key element of the link layer is that usually data can only be transmitted part of the way from the source computer to the destination computer. Wired internet, Wi-Fi, and cellular phone network are examples of link layers that can transmit data about a kilometer. Fiber optic cables, particularly those under the oceans, can transmit data to thousands of kilometers. Satellite links can also send data over long distances. Regardless of the distance we can send the data, it is still traveling over a single link, and reach the ultimate destination computer requires forwarding packets across multiple links. In this section, we will look at how one of the most common link layers functions in some detail. Wi-Fi is a great way to look at the many issues that must be solved at the link layer. We simplify some technical terms in these descriptions to make them easier to understand. So let's grab keyword. Link layer transmits data using lowest layer because it's closest to the physical network media. Connects transmits data using a wire, fiber optic cable, or a radio signal. A key element of the link layer is that usually data can be only transmitted part of the way from the source computer. Only be transmitted part of the way. Key element of link that can be only part of the way from this to the destination. Yeah. Regardless of the distance we can send it, it is still traveling over a single link, and to reach the ultimate destination computer requires forwarding packets across multiple links in this section. Okay. When your laptop or phone is using Wi-Fi to connect to the internet, it is sending and receiving data with a small, low-powered radio. The radio in your computer can only send When your laptop or phone is using a Wi-Fi to connect to the internet, it is sending and receiving data with a small, low-powered radio. The radio in your computer can only send data about 300 meters, so your computer sends your packets to the router in your home, which forwards the packets using a link to the rest of the internet. Sometimes we call the first router that handles your computer packets the base station or the gateway. All computers that are close enough to the base station with their radios turned on receive all of the packets the base station transmits, regardless of which computer the packet is supposed to be sent to. They also hear all the packets sent by every other nearby computer. So your computer needs a way to know which packets to treat as its own and which packets are being sent to other computers that can be safely ignored. An interesting side effect of the fact that all the computers within reach can hear all packets is that a root computer could also be listening to and capturing your packets. Perhaps getting a hold of important data like bank accounts, numbers, or passwords to online services. We will come back to the issue of protecting your data from prying eyes and ears in a later section. Every Wi-Fi radio in every device that is ever built is given a unique serial number at the time it is manufactured. This means that each of the computers using Wi-Fi has its own serial number, and the radio in the gateway also has a serial number. You can usually go into a settings screen on your device and look up the serial number of the Wi-Fi radio in your device. It is generally shown in the following form. This is just a representation of a 48-bit serial number of your Wi-Fi radio. It is also called Media Access Control or MAC address. A MAC address is like a forum or to address on a postcard. Every packet sent across the Wi-Fi has a source and destination address, so all of the computers know which messages are theirs. When you turn on your computer and connect to a Wi-Fi network, your computer needs to figure out which of the MAC addresses on the Wi-Fi can be used to send packets to the router. When you move from one physical location to another, your packet will be talking to different gateways, and each of those gateways will have a different serial number. So when you first connect to a new Wi-Fi, your computer must discover the MAC address for the gateway or that particular Wi-Fi. To do this, your computer sends a special message to the broadcast address, effectively asking the question, who's in charge in this Wi-Fi? Since your computer knows it is not the gateway itself, It sends a broadcast message with its own serial number as the from address and the broadcast address as the to address, to ask if there are any gateways present on the Wi-Fi network. If there is a gateway on the network, the gateway sends a message containing its serial number back to your computer. I am the gateway. Welcome to my network. If there are no replies, the computer waits a few seconds and then assumes there is no gateway for this network. When there is no gateway, your computer might show a different Wi-Fi icon or not show the Wi-Fi icon at all. Sometimes there can be more than one gateway, but we will ignore that for a while because it is a little complex and not very common. Once your computer receives a message with the MAC address of the gateway, it can use that address to send packets that it wants to get the gateway to forward the internet. From that point, all of your computer's packets have the actual serial number of the destination. You want to use the broadcast address as little as possible because every computer connected to the Wi-Fi receives and processes any messages sent to the broadcast address to make sure the messages were not intended for them. Sharing the air. Okay, so what did we learn from here? When your phone So computer needs to know, okay. An initial side of blah, blah, blah. Every Wi-Fi radio in every device that is ever built is given a unique serial number. Are you kidding me? You can go into your settings screen on your device and look up the serial number of the Wi-Fi. It's generally shown in the form of... Okay. So MAC address we use only for, apparently, for Wi-Fi, for wireless connection, media access control. Every packet sent across the Wi-Fi has a source and destination address, so all of the computers know which messages are theirs. When you turn on your computer and connect to a Wi-Fi network, your computer needs to figure out which of the MAC addresses on the Wi-Fi can be used to send packets to the router. When you move from one physical location to another, your computer will be talking to different gateways, and each of those gateways will have a different serial number. So when you first connect to a new Wi-Fi, your computer must discover the MAC address for the gateway of that particular Wi-Fi. To do this, your computer sends a special message to broadcast address, effectively asking the question. So it knows it is not the gateway itself, it sends a broadcast message. It is on... Since your computer knows it is not the gateway itself, it sends a broadcast message with its own serial number as the from address and the broadcast address as the to address to ask, oh my god. You want to use the broadcast address as little as possible because every computer connected to the Wi-Fi receives and processes any messages sent to the broadcast address to make sure the messages were not input for them. Where is the broadcast address? Aha, yeah, I got it. Yeah, okay. So the broadcast address itself is this one. I still have 5 minutes. I still have 5 minutes. But see, that's what I'm talking about. This is the part. This is exactly the part which is the learning. We are getting familiar with the terms. See, this is exactly what I'm talking about. That's the whole point. Because we are now asking the question. We are already knew, like MAC address, I already was aware, but why? Like now we can actually imagine like how these things are working. And so if I understand correctly, the broadcast address is what is the broadcast address? Can we ask ChatGPT? Man, it's so cold though. It's so cold. Are you kidding me? Okay, I cannot log into ChatGPT. Jesus Christ, what the hell? Ah, okay, I know what's the problem. Okay. All right, so anyway, MAC address, MAC gateway, broadcast address. Okay, break time. Okay, this is gonna be a little bit longer break because I have to do some other stuff as well, some bathroom stuff. So let's make it 10 minutes. Yeah, I really need to use the bathroom, absolutely. So let's do 10 minutes. Hopefully it's gonna be enough. All right, so that was a huge break. I overlapped it with 8 minutes according to the plan. So this is not how we should be doing things. So negative points for you, Gergely, negative points. But anyway, so it was 11:30. It's been 2 hours since the 10 milligrams. It's been 2 hours. What is our impression so far? So basically, as I was coming up, as I was reading the very beginning, I felt like the discomfort hit in, like just, when your mind is trying to attack you with your, about situations, about stuff, emotions, which are not relevant to the current moment, because like you can distance yourself from things that bothering you, because like what we are dealing with now is what matters, right? Like this is the actual thing that's gonna create change. And through this, you can get somewhere, and then you can have new experiences in life and everything, which will be, you're gonna tackle them much more efficiently because you are able to focus, right? That's the only thing, is like no matter what, you are able to focus. And it's just sometimes so hard. It's really hard. Yeah, really, really, really. This is like such a mind game. Anyway, so let me use the phone, or I mean the watch. 25 minutes. We continue. So where did we stop? When moving to a new location, your computer first sends a special message to the broadcast. And I wanted to ask ChatGPT if the broadcast address is always the same. Is it always the same? Or it's not? Okay, so yeah. I'm gonna just take this part and ask, because I think I misunderstood. Broadcast address is not the MAC address. In the message you provided, the broadcast address is indeed FFFFF. This MAC address is used as a destination address in the Internet frames when broadcasting a message to all devices on the local area next segment. So in this case, the broadcast message is being sent to all devices on the network, effectively asking if there are any gateways present. If there is a gateway on the network, the gateway sends a message containing its serial number back to your computer. I'm so happy that my cat is calm and not bothering me. She's so nice. If there are no replies, your computer waits a few seconds and then assumes there is no gateway for this network. When there is no gateway, your computer might show, if there is no gateway, your computer might show a different Wi-Fi icon or not show the Wi-Fi icon at all. Sometimes there can be more than one gateway. Once your computer receives a message with the MAC address on the gateway, it can use, yeah, exactly. and didn't receive a response yet. So when we are troubleshooting a technical network issue, we are basically looking for the media access control gateway, and we are looking for this address, and that's pretty much it. We should not use the broadcast address. The broadcast address, the special broadcast address should only be used for searching the MAC gateway. So basically there's no privacy at all. Everybody knows everything, like if you really want to. But anyway, let's move on. Courtesy and coordination. Because many computers are sharing the same radio frequencies, it's important to coordinate how they can send data. When there's a crowd of people in a room, they can't all talk at the same time, or everything will be garbled. The same thing happens when multiple Wi-Fi radios transmit at the same time on the same frequency. So we need some way to coordinate all the radios to make best use of the shared frequencies. We will look at the basics of technical approaches to avoiding lost data due to transmission collisions. The first technique is called the carrier sense, which we talked about it. This technique is to first listen for a transmission, and if there is already a transmission in progress, wait until the transmission finishes. It might seem like you could wait for a long time, but since all messages are broken into packets, usually your computer only has to wait for the computer currently sending data to finish a packet, after your computer gets its chance to send data. If your computer's Wi-Fi radio listens for data and hears silence, it can begin transmitting. But what if another computer's Wi-Fi radio that wants to send a packet listened to and heard the same silence and decided to start transmitting at exactly the same time? If two or more Wi-Fi radios start transmitting at the same time, all of the data is corrupted and both packets are lost. So once your Wi-Fi radio starts sending a packet, it is important for it to listen to make sure it can receive its own data. If it is not receiving the same thing that is sending, your Wi-Fi radio assumes that a collision has happened. This is called the collision detection, and stops transmitting since it knows that no data will be received by the destination Wi-Fi radio. We humans do a similar thing in a room full of people. When two people start talking at the same time, they are good at noticing that another person is talking and quickly stop talking. But the problem is how to restart the conversation. After a long pause, it is common that both people start talking at the same time again. This can happen over and over, and each person says "no, you" repeatedly to figure out how to get the conversation restarted. It can be quite comical at the same time. The Wi-Fi radios in two computers that send colliding packets are able to solve this problem much better than people can solve the problem. When the Wi-Fi radios detect a collision or garbled transmission, they compute a random amount of time to wait before retrying the transmission. The rules of computing the random weight are set up to make sure the two colliding stations pick different amounts of time to wait before attempting to retransmit the packet. The formal name for the listen, transmit, listen, and wait and retry if necessary is called carrier sense multiple access with collision detection, or CMACD. It might sound a little chaotic to just give it a try and then give it another try if your transmission collides with another station's transmission, but in practice it works well. There is a whole category of link layers that use this basic pattern of listen, transmit, listen, and optional retry. Wired internet, cellular telephone data, and even short message are all use this. Cool. Dum dum tak da da dum dum da 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 dum da. I'm back. All right, okay. Jesus. Because many computers, when there's a crowd, the same thing happen. We will look at the basics of technical approaches to avoiding lost data due to transmission collisions. Don don ta da da don don ta da da don don ta da don ta down bam 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 ba ba bam bam ba bam bam ba da da don da don. This listen, yeah, it might seem like, yeah, if your computers, what if then, so once, okay. If two or more Wi-Fi radios start transmitting at the same, what if another computers, yes. But I thought this is not in the link layer. I thought this is already above somewhere else. At the same time, it listens if the data is received. If it's not receiving the same But I thought, okay, so my question from here is that why can we send simultaneously over the network? Why we can only do once? Why we have to wait? That's so strange. Bam bam ba da dun dun da 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 dun dun da da dun da down da da down 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 da da dun dun da da dun dun da. Coordination in other link layers. Sometimes when a link layer has many transmitting stations and needs to operate at near 100% efficiency for long periods of time, the design takes a different approach. In this approach, there is a token that indicates when each station is given the opportunity to transmit data. Stations cannot start a transmission unless they have the token. Instead of listening for silence and jumping in, they must wait for their turn to come around. When a station receives the token and has a packet to send, it sends the packet. Once the packet has been sent, the station gives up the token and waits until the token comes back to it. If none of the stations have any data to send, the token is moved from one computer to the next computer as quickly as possible. A group of people sitting around a meeting could communicate without ever interrupting each other by having a small ball they pass, the Tekken ball, they pass around in a circle, only allowing the person who has the ball to speak. When you get the ball and have something to say, you talk for a short period and then pass the ball on. The try and retry CMA CD/CD approach works very well when there is no data or when a low or moderate levels of data are being sent. But on a token style network, if there is no data being sent and you want to send a packet, you still have to wait. Oh no. You still have to wait a while before receiving the token and can start transmitting. When you finish your packet, you have to wait until the token comes back before you can send the next packet. If you are the only station that wants to send data, you spend a good bit of time waiting for the token to come back to you after pressing through all of the other stations. The token approach is best suited when using a link medium such as a satellite link or an undersea fiber optic link, where it might take too long or be too costly to detect collision. The carrier sense multiple access with collision detection is best suited when the medium is inexpensive, shorter distance, and there are a lot of stations sharing the medium that only sends data in short bursts. So that's why Wi-Fi is so effective for providing network access in coffee shop, home, or room in a school. Now that we have looked at the lowest layer in a 4-layer architecture and we have only taken a simple look. So now we have taken a look. Okay, and we only have taken a simple look at how the link layer works. There are many other details that must be designed into link layer, like connection, distance, voltage, frequency, speed, and many others. A key benefit of layered architecture is that engineers who design and build link layers technologies can ignore all of the issues that are handled by layers above the link layer. This allows them to focus on building the best solution to moving data across a single hop. Modern day link layers like Wi-Fi, satellite, cable modems, internet, and cellular technology are very well developed. Data moves so quickly and seamlessly that once we get our connection, we rarely have to worry about the link layer. It just works. Look at that guy. Okay, so this is the part where the Pomodoro wouldn't help, because in 1 minute I should have a break, but I don't feel like I have enough. So let me make a note of this part, this link layer. Let's make the test. There will be some test, right? Or questions, quiz, and then we can have another break. And I have to really think about the lunch, when it's gonna be ideal to have the lunch, because I want to, next dose should be at 3 p.m. 3 p.m. 30 minutes, 3:30. But I don't know. Yeah, really, I don't know if I should, stop the stream or anything. I think I should keep the stream on, because this is something that holds us accountable. So I could just, keep the stream on. Keep the stream on. I eat after the next break, 2:30. I'm sorry, I have to do this like this. I have to make a plan, because many times really it's about food, eating something, and then it's, you know, you lose control over your brain like so easily, and it always happens around food. Yeah, food has a very big connection with how your brain works, and you know, that's why I think many tech people just don't eat at all, because they know that, you know, they basically operate on a different level, and it's actually stopping you from paying attention, being able to focus. So, but I have nice little food now. Nothing. I don't want to be that person, to be honest. I think it's important to eat. But yeah, 2:30 I can have a meal. Then it's 1 hour of just. But we still continue, and yeah. And then another one. And yeah, in the evening I will go. In the evening I will go out. I will pick up my stuff. And everything. Right, Kat? What do you think? Sometimes when a link layer has many transmitting stations and needs to operate at nearly 100% efficiency for long periods of time, design takes a different approach. In this approach, there is a token. What a horrible weather. Oh my god. But the best time for this, what we are for this kind of activity, what we are doing, it's the best. Okay, so the glossary, we have base station, we have broadcast, connected to the will receive broadcast, sending a packet in a way that all the stations, let's write something there. Base station, PlayStation. Okay, question time. I think we can go through all of this weekend. I think this is gonna be quite short. It's an introduction, and by the way, it's an introduction, and that was our goal. We have an introduction part, and then we should really look into deeply about the technologies like which we use. But yeah. Anyway, when using a Wi-Fi network to talk to the internet, where does your computer send its packets? When using a Wi-Fi network to talk to the internet, where does your computer send its packets? How is the link physical address for the is assigned? By the manufacturer of the link equipment. Which of these is a link address? Wait, but why would you say link address when it's MAC address? It's not clear. But I guess this is what you mean. How does your computer find the gateway on the Wi-Fi network? It has a gateway address. How does your find? It sends a message to all possible get onto the find. It broadcasts. Okay. It broadcasts a request for the address of the gateway. When your computer wants to send data across Wi-Fi, what is the first thing? Send a message, listens to the... Listen. What does a Wi-Fi connected workstation do when it tries to send data and senses a collision has happened? Keep sending the message so part of the message makes it through. Wait until told by gateway that collision is over. Immediately restart transmitting the message at the beginning. Okay, wait. What does a Wi-Fi connected workstation do when it tries to send data and sense collision? Keep sending the message so... Exactly. When a station wants to send data across a token style network, what is the first thing it must do? We got this. Okay, so now it's like a good almost an hour break I'm gonna have, but I will keep the stream because why not? So I'm gonna put, I should put some, I cannot put YouTube on because I remember they had an issue with this. So I'm not gonna put YouTube on, but I'm gonna put some, yeah, the jazz music again and the timer, of course. I don't care. Zappa. All right, we are back. Very nice break. Super nice, productive. There's a lot of mess behind me, but please ignore that. But yeah, very nice break. I went to the balcony to eat. Very cold, but I had my little winter jacket. The cat came out and said, like, was watching me while I'm eating, so I wasn't alone. And I'm still limiting social media use even now. Like, I really opened it and just really checked for crucial information, like crucial, text, which is really important. And I checked it, I answered, and I used Duolingo, and very nice. And for the rest of my break, I was playing guitar and trying to get this. I have this looper. It's very nice. Like, I have it for over 2 years, I think, and now I finally read the manual that how you can actually make songs. Like, you have 12 slots for different songs. It's actually very nice, very, very interesting, and I'm looking forward for the next break so I can play more with it. But anyway, with that said, let's go and let's see the internetworking layer. I lost the yeah, because this is not the one, this is the one. Boom. So yeah, 25 minutes. So this is gonna be completely on during digesting process. So 25 minutes, but at 5:30 we're gonna get our second dose, and this is very, very important and crucial. Really, I cannot tell you how much is it important that you respect the 4-hour gap, because this is how you can use it to your own advantage. And if you start messing around with random doses and everything, this is when we lose the effectiveness, I would say. Everything is ready, let's go. Now that we can move data across a single link, it's time to figure out how to move it across the country or around the world. To send data from your computer to any of a billion destinations, the data needs to be moved across multiple hops and across multiple networks. When you travel from your home to a distant destination, you might walk from your home to a bus stop, take a train to the city, take another train to the airport, take a plane to a different airport, take a taxi into the city, then take a train to a smaller town, a bus to even a smaller town, and finally walk from the bus stop to your hotel. A packet also needs to take multiple forms of transportation to reach its destination. For a packet taking its trip to another country, the walk, bus, train, and plane can be thought of as different link layers like Wi-Fi, internet fiber, and satellite. At each point during the trip, you or your packet are being transported using a shared medium. There might be hundreds of other people on the same bus, train, or plane, but your trip is different from that of every other traveler because of the destination decisions that you make at the end of each of your hops. For instance, when you arrive at a train station, you might get off one train, then walk through the station and select a particular outbound train to continue your journey. Travelers with different starting points and destinations make a different series of choices. All of the choices you make during your trip result in you following a series of links or hops along a route that takes you from your starting point to your destination. As your packet travels from its starting point to its destination, it also passes through a number of stations where a decision is made as to which output link your packet will be forwarded on. For packets, we call these places routers. Like train stations, routers have many incoming and outgoing links. Some links may be fiber optic, others may be satellite, and still others might be wireless. The job of the router is to make sure packets move through the router and end up on the correct outbound link layer. A typical packet passes through from 5 to 20 routers as it moves on from its source to its destination. But unlike a train station where you need to look at displays to figure out the next train you need to take, the router looks at the destination address, to decide which outbound link your packet needs to take. It is as if a train station employee met every single person getting off an inbound train, asked them where they headed, and escort them to the next train. If you were a packet, you would never have to look at another screen with a list of trains the person tracks. The router is able to quickly determine the outbound link from your packet because every single packet is marked with its ultimate destination address. This is called the Internet Protocol address, or IP address for short. We carefully construct IP addresses to make the routing job of the... Wow, okay, so that's very cool. So what is the key takeaway from this section? In the previous section, where we talked about link layer addresses, we said that link addresses were assigned when the hardware was manufactured and stayed the same throughout the life of a computer. We cannot use link addresses to route packets across multiple networks because there is no relationship between a link layer address and the location where the computer is connected. So the link layer address is the same as MAC address. I just don't like when they making up stuff. Link layer address Yes, in most cases when people refer to link layer address in the context of internet, they are referring to the MAC address. We said that link addresses were assigned when the hardware was manufactured and stayed we cannot use because there's no relationship between link address and the location where the computer is connected to the network. With portable computers and cell phones moving constantly, the system would need to track each individual computer as it moves from one location to another. And with billions of computers on the network, using the link layer address to make routing decisions would be slow and inefficient. To make this easier, we assign another address to every computer based on where the computer is connected to the network. There are two different versions of IP addresses. The old, classic IPv4 addresses consist of 4 numbers separated by dots like this. Each of the numbers can only be from 0 to 255. We have so many computers connected to the internet now that we are running out of IPv4 addresses to assign them. IPv6 addresses are longer and look like this. Oh my god. For this section, we will focus on the classic IPv4 addresses, but all of the ideas apply equally to the IPv4 and IPv6 addresses. Most important thing about IP addresses is that they can be broken into 2 parts. What is this? There are many points where an IP address can be into network number and host. For example, we just split the address in half. Each of the numbers can only be from 0 through 255. This is very important. But why is it 6? 1, 2, 3, 4, 5, 6. It's even more. 1, 2, 3, 1, 2, 3, 4. Yeah, this is 6. So it doesn't make any sense to call this IPv6. You should call them IPv8. So to make it harder. But anyway. The idea is that many computers can be connected via a single connection to the internet. An entire college campus, school, or business could connect using a single network number or only a few network numbers. In this example above, 65,536 computers could be connected to the network using the network number of 212. Since all of the computers appear to the rest of the internet on a single connection, all packets with an IP address of 222 can be routed to the same location. By using this approach of a network number and host identifier, the routers no longer have to keep track of billions of individual computers. Instead, they need to keep track of perhaps 1 million or less different network numbers. So when your packet arrives in a router and the router needs to decide which outbound link to send your address to, the router does not have to look at the entire IP address. It only needs to look at the first part of the address. That's very cool, actually. Okay, break time. Yeah, and it's 3 p.m. So 3 p.m. 30. 3:30 p.m. Sorry. How can I add another one? how routers determine routes. Okay, sorry, that was too loud. How those little... Okay, wait, I didn't pause this guy. While the idea of the collapsing many IP addresses into a single network number greatly reduces the number of individual endpoints, the router must track... I'm gonna fall apart one day. I feel like it. Oh my god. So anyway, the number of the router must track to properly route. Okay, wait. While the idea of collapsing many IP addresses into a single network number greatly reduces the number of individual endpoints the router must track to properly route packets, each router still needs a way to learn the path from itself to each of the network number it might encounter. When a new core router is connected to the internet, it does not know all the routes. It may know a few pre-configured routes, but to build a picture of how the packets, it must discover how to route packets, it must discover routes as it encounters packets. When a router encounters a packet that it does not already know how to route, it queries the routers that are its neighbors. The neighboring routers that know how to route the network number send their data back to the requesting router. Sometimes neighboring routers need to ask their neighbors and so on until the route is Sometimes the neighboring routers need to ask their neighbors and so on until the route is actually found and sent back to the requesting router. In the simple case, a new core router can be connected to the internet and slowly build a map of network numbers to outbound links so it can properly route packets based on the IP addresses of each incoming packet. We call this mapping of network numbers to outbound links to the routing table for a particular router. Okay, so basically, when a new core router is connected to the internet, it does not know all the routes. It may know, but to build, it must discover. So yes, it makes sense. When a router encounters a packet that it has already not know how to route, that it does not already know how to route, it queries the routers that are its neighbors. When the internet is running normally, each router... Did I even set up the timer? Oof, I forgot. I forgot. Okay, so we will do it from now. So 25 minutes again. When the internet is running normally, each router has a relatively complete routing table and rarely encounters a new network number. Once a router figures out the route to a new network number, the first time it sees a packet that's distinct for that network number, it does not need to rediscover the route for the network number unless something changes or goes wrong. This means that the router does a lookup on the first packet, but then it could route to the next billion packets to that network number just by using the information it already has in its routing table. This means that the route does a lookup on the first packet, but then it could route to the network not just by using the information. Sometimes the network has problems and the router must find a way to route data around the problems. A common problem is that one of the outbound links fails. Perhaps someone tripped over a wire and unplugged a fiber optic cable. At this point, the router has a bunch of network numbers that it wants to route out a link on a link that has failed. The recovery when a router loses an outbound link is surprisingly simple. Oh my god, this got so expensive. Oh my god, this wasn't this expensive. Jesus Christ. I don't remember paying so much. Yeah, I'm losing control, I know, but I'm just trying to figure out something. Can ChatGPT? Oh my god, 7,000. Oh my god, inflation is crazy. For example, if you want a 2-part bar to play for 4 bars, or you want the same verse to play before and set, press each part button in this desired sequence order. Note that you can sequence the same part multiple times. Press the sequence, the button. Playback of the various parts that can make up song can be ordered and automated by creating a song sequence. This allows you to focus on your playing rather than manually switching song part. Press the sequence button. The button will begin. Press each part in the desired sequence order. Note that you can sequence the same part multiple times. Got it. Sometimes the network has problems and a router must find a way to route data around the problems. A common problem is that one of the outbound links fails. Perhaps someone tripped over a wire and unplugged a fiber optic cable. At this point, the router has a bunch of network numbers that it wants to route out on a link that has failed. The recovery when a router loses an outbound link is surprisingly simple. The router discards all of these entries in its routing table that were being routed on that link. Then as more packets arrive for those network numbers, the router goes through the route discovery process again, this time asking all the neighboring routers except the ones that can no longer be contacted due to the broken link. Excuse me. Oh my god, no focus. Oh my god. The router discards. The router, okay, the solution is very simple because the router discards all of the entries in the routing table that were being routed on that link. Then, as more packets arrive for those network numbers, the router goes through the route discovery process again, this time asking all the neighboring routers except the ones that can no longer be contacted due to the broken link. This is why it is important for there to be always be at least two independent paths from a source network to a destination network in the core of the network. Wow, I'm so red. But I hope in real life I'm not this red. Jesus. I think this is just the color of the whatever. Nice, I like this better. This is very nice. At some point the broken link is separated or a new link is brought up and the router wants to make best use of the new links. The router is always interested in improving its routing tables and looks for opportunities to improve its routing tables in its spare time. When there is a lull in the communication, a router will ask a neighboring router for all or part of its routing table. The router looks through the neighbor's tables, and if it looks like the other router has a better route to a particular network number, it updates its network table to forward packets for that network number through the link to the router that has a better route. With these approaches, the outages and the exchange of routing table information, routers can quickly react to network outages and reroute packets from links that are down or slow to links that are up and or faster. All the while, each router is talking to its neighboring routers to find ways to improve its own routing table. Even though there is no central source of the best route from any source to any destination, the routers are good at knowing the fast the routers are good at knowing the fastest path from a source to a destination nearly all the time. Routers are also good at detecting and dynamically routing packets around links that are slow or temporarily overloaded. One of the side effects of the way routers discover the structure of the network is that the route your packets take from the source to destination can change over time. You can even send one packet immediately followed up by another packet, and because of how the packets are routed, the second packet might arrive at the destination before the first packet. We don't ask the IP layer to worry about the order of the packets, it has already enough to worry about. We pour our packets with source and destination IP addresses into the internet, much like we would send out a bunch of letters in the mail at the post office. The packets each find their way through the system and arrive at their destinations. Ja, Istenkém. Okay, 3 minutes. 3 minutes. Yeah, this dynamic routing. Lol. Yeah, I mean, I don't know this part, literally, like, what can I say in my words, really, here? Okay, when there's nothing, when there's silence, lull in communication. I don't even know what do you mean when there's a lull in communication. Lull is ripple silence or decrease in exchange messages. Yeah, exactly. So when there's silence, the router will ask neighboring routers for all or parts of its routing table and updates it. With these approaches to outages and the exchange of routing table, routers can quickly react to network outages. we pour our packets with source and destination IP into the internet, much like we would. The packets each find their way through the system and arrive at their destinations. Perfect, very nice. So this is the when things get okay. This is all, the whole chapter 4 is about internetworking layer, okay? So just saying, this is all about internetworking layer. So yeah, when something falls, yeah, we basically understand how the router is inside, what's happening inside, and they are very intelligent beings, I would even say so, because they're always looking. And so there are two, but this two connected network, this is why it's super duper important for at least two independent paths from source network to destination network, two possible independent routes. These breaks are getting shorter and shorter, guys. Oh. Yeah, I would say so. This second dose is not really working out for now, but whatever. So everything is back. Let's go. There's no place in the internet that knows. Yeah, I think I'm messing up my break again because so what I started to do now in the breaks is that I'm trying to use the digital Trio Plus, right? Digitech Trio Plus, and yeah, I'm just discovering new functions, new things I can do with it, with the sequencing and everything, and I'm also trying to play something good in C major scale, like combining these. And this is not relaxed, these 5 minutes should be spent with trying to something new. Like, you can use your guitar, of course, definitely not social media or anything like that, but something which is like something, you can just you don't have to even think about chords, just play, or I don't know, or play a scale if that's something that makes you need to do something which is it's really about chill out brain, right? So yeah, just food of thought. There is no place in the internet that knows in advance the route your packets will take from your computer to a particular destination. Even the routers that participate in forwarding your packets across the internet do not know the entire route your packet will take. They only know which link to your packets, which link to send your packets to so they get closer to their final destination. But it turns out that most computers have a network diagnostic tool called traceroute or tracer, depending on the operating system. That allows you to trace the route between your computer and the destination computer. Given that the route between any two computers can change, I need to set up the timer. Given that the route between any two computers can change from one packet to another, when we trace a route, it is only a pretty good guess as to the actual route packets will take. The traceroute command does not actually trace your packet at all. It takes advantage of a feature in the IP network protocol that was designed to avoid packets becoming trapped in the network and never reaching their destination. Before we take a look at traceroute, let's take a quick look at how a packet might get trapped in the network forever and how the IP protocol solves that problem. Remember that the information in any single router is imperfect, and it is only an approximation of the best outbound link for a particular network number, and each router has no way of knowing what any other router will do. But what if we had 3 routers with a routing table entries that formed an endless loop? Each of the routers knows the best outbound link for IP addresses starts with 212.78. But somehow the routers are a little confused and the routing tables form a loop. If a packet with a prefix of 212.78 found its way into one of these routers, it would be routed around a circle of 3 links forever. There is no way out. As more packets arrive with the same prefix, they would just be added to this infinite packet vortex. Pretty soon the links would be full of traffic going round and round. The routers would fill up with packets waiting to be sent, and all 3 routers would crash. The problem is worse than having someone trip over a fiber optic cable, since it can cause several routers to crash. Oh shit. To solve this problem, the Internet Protocol designers added the number of each packet that called time to live. This number starts out with a value of about 30. Each time an IP packet is forwarded down a link, the router subtracts 1 from the TTL value. So if the packet takes 15 hops to cross the internet, it will emerge on the far end with a TTL of 15. But now let's look at how the TTL functions when there's a routing loop or packet vortex for a particular network number. Since the packet keeps getting forwarded around the loop, eventually the TTL reaches 0. And when the TTL reaches 0, the router assumes that something is wrong and throws the packet away. This approach ensures that routing loops do not bring whole areas of the network down. So that is a pretty cool bit of network protocol engineering. To detect and recover from routing loops, we just put a number in, subtracts 1 from that number on each link, and when the number goes to 0, throw the packet away. It also turns out that when the router throws a packet away, it usually sends back a courtesy notification, something like, "Sorry, I had to throw your packet away." The message includes the IP address of the router that threw the packet away. Okay, this part is super heavy. Oh my god. Okay, this part is super heavy. It's not even counting. Okay. Phew, now we should have a coffee. Now it would be rice. I'm gonna just make like I pause now. I'm gonna make a coffee and we're gonna continue. Like actual coffee time. Somebody should make a channel with AI generated relax music. Wow, I can't even imagine, like, it's so scary to think about that, the amount of content which is just gonna come, and but not actually, somebody didn't actually take their time to think it through. It's just like, here you go. Anyway, I'm gonna start a new 25 minutes. Very shitty coffee. 1 2 3 4 1 2 3 4. Let's go. So I'm gonna go step by step again here, because there's no place in internet. I forgot what is the thing. Jesus Christ. Okay, I think that's our cue that I'm lost at. Jesus. Ah, that's very cool. Okay, so that's very nice. This is so cool information. This is super nice, guys. Like, this is super nice. Where can I find this? Network loops are usually pretty rare. Network loops are usually pretty rare, but we can use this notification that a packet was dropped to map the approximate route a packet takes through the network. The tracer route program sends packets in a tricky manner to get the routers that your packets pass through to send it back. Not what? The tracer route program sends packets in a tricky manner to get the routers that your packets pass through to send it back notifications. First, tracer route sends a packet with a TTL of 1. The packet gets to the first router and is discarded, and your computer gets a notification from the first router. Then tracer route sends a packet with a TTL of 2. The packet makes it through the first router With this approach, Tracer route builds up an approximate path that your packets are taking across the network. It took 14 hops to get from Ann Arbor, Michigan to Palo Alto, California. The packets pass through Kansas, Texas, Los Angeles, in Oakland. This might not be the best route between the two cities if you are driving a car or taking a train, but on that day, for packets between the two cities, this was the best route. This is very interesting. Oh my god. Okay, I'm gonna check this out. So we're gonna check this out right now. This is super cool. So we're just gonna use tracer route. So what website we should check? Can I just put the Dr. Chuck website? This is super interesting. See, that's what I'm talking about. There's always something which is like actually like you're looking into the things. So this is like, okay, anyway, Devon.Dr. Chuck. Wow, haha, this is so cool. Look at this. Sometimes a trace route can take a little while, up to a minute or two. Not all routers will give you the "I discarded your ticket" message. In the example above, the router at hop 13 threw our packet away without saying "I'm sorry." Yeah. Request timed out. Yeah, I see. Request timed out. Traceroute waits for the message and after a few seconds just gives up and increases the TTL value so it gets past the root router. If you run a traceroute for a connection that includes an undersea cable, you can see how fast data moves under the sea. Here is a traceroute between the University of Michigan and Peking University in China. You can see when packet is encountering a long undersea cable in steps 7 and 8. The time goes from less than 1.10 seconds to okay. Very impressive. This coffee was good coffee. Yeah, after all. Why does it take so long to get the voiceover? You can see when the packet is encountering a long undersea cable in steps 7 and 8. 7 and 8. Or here, 7 and 8. If you run a traceroute connection, here's a traceroute between University of Michigan and Peking in China. So this is the one. Okay, this is the example. You can see when the packet is encountering a long undersea cable in steps 7 and 8. The time goes from less than 1/10 of a second to nearly 1/4 of a second. Even though 1/4 of a second is slower than 1/10, it's still pretty impressive when you consider the packet is going nearly all of the way around in the world in that 1/4 second. The core of our internet protocol network is remarkable. Most of the time we don't really care how hard the routers are working to make sure our packets move quickly. from our computer to the various destinations around the world. We will move from looking at how the core of the network functions and how internet protocol addresses are managed at the edges. Yeah, cool. Makes sense. Fair enough. Yeah, this is very interesting part. So, break time. how far we go today, that's the big question, really. How far we go. That would be nice to determine. And what is this light now? Very strange. It's getting darker, I guess. Ah. Increasingly, okay, 25 minutes. Why are you doing this? I have no idea. Ah, okay, I understand everything. I understand everything. Increasingly, computers are portable or mobile. We just pointed out how important it was for the IP layer to track large groups of computers using network numbers instead of tracking every single computer individually. But since these network numbers indicate a particular physical connection to the network, when we move a computer from one location to another, it will need a new IP address. Remember that the link layer addresses is set when a computer is manufactured and never changes throughout the life of the computer. If you close your laptop in one coffee shop and reopen it using your home Wi-Fi, your computer will need a different IP address. This ability for your computer to get a different IP address when it is moved from one network to another uses a protocol called Dynamic Host Configuration Protocol, DHCP for short. DHCP is pretty simple. Going back to the link layer section, recall the first thing your computer does at a link level is ask, is there a base station on this network, by sending a message to the special broadcast address. Once your computer is successfully connected to the link at the link layer through that base station, it sends another broadcast message, this time asking, is there a gateway connected to this network that can get me onto the internet? If there is, tell me your IP address and tell me what IPs I should use on this network. When the gateway router replies, your computer is given a temporary IP address to use on that network. For instance, while you're at a coffee shop. After the router has not heard from your computer for a while, it decides you are gone and loans the IP address to another computer. If this process of reusing a loaned IP address goes wrong, two computers end up on the same network with the same IP address. Perhaps you have seen a message on your computer to the effect of, another computer is using this IP address, we have stopped using this address. Your computer sees another computer with a link address other than its own, using the IP address that your computer thinks it's assigned to it. But most of the time, this dynamic IP address assignment, DHCP, works perfectly. You open your laptop and in a few seconds you're connected and can use the internet. Then you close your laptop and go to a different location and given a different IP address to use that location. In some operating systems, when a computer connects to a network, issues a DHCP request and receives no answer, it decides to assign itself an IP address anyway. Often these self-assigned addresses starts with 169. When your computer has one of these self-assigned IP addresses, it thinks it is connected to a network and has an IP address but without a gateway. It has no possibility of getting packets routed across the local network and onto the internet. The best that can be done is that a few computers can connect to a local network, find each other and play a network game. There's not much else that can be done with these self-assigned IP addresses. If you know how to find the IP address on your laptop, you can do a little experiment and look at different IP addresses you get at different locations. If you made a list of the different addresses you received at different locations, you might find that many of the locations give out addresses with a prefix of 192.168. This seems to be a violation of the rule that the network number IP address prefix is tied to the place where the computer is connected to the internet, but a different rule applies to addresses that starts with 192.168. This means that they will never be used as a real addresses that will route data across the core of the network. They can be used within a single local network, but not used on the global network. So then how is that your computer gets an address like 192 blah 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 on your home network and it works perfectly well on the overall internet? This is because your home router gateway base station is doing something we call network address translation, or NAT. The gateway has a single routable IP address that is sharing across multiple workstations that are connected to the gateway. Your computer uses its non-routable address like blah 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 to send its packets, but as the packets move across the gateway replaces the address with actual routable addresses. When packets come back to your workstation, the router puts your workstation's non-routable address back into the returning packets. This approach allows us to conserve the real routable addresses and use the same non-routable addresses over and over for workstations that move from one network to another. So weird. if you wanted to construct, everything is set up, right? Okay. If you wanted to connect the network for a new organization to the internet, you would need to contact an internet service provider and make a connection. Your ISP would give you a range of IP addresses that you, one or more networks now, that you could allocate to the computers attached to your network. The ISP assigns you network numbers by giving you a portion of the network numbers they receive from a higher level service provider. The ISP assigns you network numbers by giving you a portion of the numbers they receive on a higher level internet service provider. At the top level of IP address locations are 5 regional internet registries, RIRS. Each of the 5 registries allocates IP addresses for a major geographic area. Between the 5 registries, every location in the world can allocate a network number. The 5 registries are North America, South and Central America, Europe, Asia Pacific, and Africa. When the classic IPv4 addresses were invented, only a few thousand computers were connected to the internet. We never imagined that someday we would have a billion computers on the internet. But today, with expansions of the internet and Internet of Things, where smart cars, refrigerators, thermostats, and even lights will need IP addresses, we need to connect far more than a billion computers to the internet. To make it possible to connect all these new computers to the internet, engineers have designed a new generation of the internet called IPv6. The 128-bit IPv6 addresses are much longer than the 32-bit IPv4 addresses. The regional internet registries are leading the transition from IPv4 to IPv6. The transition from IPv4 to IPv6 will take many years. During that time, both IPv4 and IPv6 must work seamlessly together. The internetworking protocol layer extends our network from a The internetworking protocol layer extends our network from a single hop link layer to a series of hops that results in packets quickly and efficiently being routed from your computer to a destination IP address and back to your computer. The IP layer is designed to react and route around network outages and maintain near identical routing paths for packets moving between billions of computers with any kind of central routing clearinghouse. Each router learns its position within the overall network and by cooperating with its neighboring routers helps move packets efficiently across the internet. The IP layer is not 100% reliable. Packets can be lost due to momentary outages or because the network is momentarily confused about the path that a packet needs to take across the network. Packets that your system sends later can find a quicker route through the network and arrive before packets that your system sent earlier. It might seem tempting to design the IP layer so that it never loses packets and ensures that packets arrive in order, but this would make it nearly impossible for the IP layer to handle the extreme complexities involved in connecting so many systems. So instead of asking too much of the IP layer, we leave the problem of packet loss and packets that arrive out of order to our next layer up, the transport layer. The transport layer. The transport layer. I was too enthusiastic about the transport layer. Lol. Can I clip that? Let's clip that right now. Oh my god, okay, so So the internetworking protocol layer lives directly in the router. It basically exists in the router. It's part of every router, and it's the job of doing, all kinds of stuff. Okay, let's write down the glossary. Maybe it's not maybe it's not the base station. Maybe it's the edge router is the base station. I have no idea. Anyway. Question time. Question time. Let's see. What is the goal of the internetworking layer? Move packets across multiple hops from a source to destination computer. Oh, I'm so dead. Okay. Move packets across multiple hops from a source to destination computer. Move packets across a single, no, from hops. Exactly. That's the main goal. How many different physical links does a typical packet cross from its source to destination? How many different physical links? Physical links. What are you talking about? Well, khanacademy.com. I know Khan Academy. That was 10 years ago when I started to learn about DNA and everything. Ooh, that was very. See, I had potential. I had potential. I just never used it. Why is it necessary to move from IPv4? Because we don't have any IPv4. What is a network number? The group, the first part of the, with the same, yes, exactly, that's the one. How many computers can have addresses within network number of this one? Oh my god. Let's do 65,000. How do routers determine the path taken by a packet across the internet? Yes, exactly. What is a routing table? A list of IP addresses mapped to link addresses. A list of networks mapped to the other links of the route. I guess that's the one. How does a newly connected router fill its routing tables? By checking the neighboring routers. Request for comments. I remember request for comments, but not that one. What does a router do when a physical link goes down? What does a router do when a physical link goes down? Throws away all of the routing table entries for that link, sends all the packets for that link back to the source computer. I think I would throw away all the routing table entries for that link. Or send it back. No, it actually doesn't send it back because it just says, sorry, it didn't. I would say throw away, but I think that's also true. Why is it good to have at least two connected networks? Because it removes the need, it continues even, yeah, exactly. Do all packets from a message take the same route across the internet? No. How do routers discover new routes and improving their routing tables? They periodically ask neighboring, what is the purpose of time to live? To make sure do not end up in the hole, in the infinite loop. How does the traceroute command works? It sends a series of packets with two data values so it can get exactly. How long does it take for a packet to, who needs this? I don't think anybody needs this, to be honest. This is such a unnecessary for a packet to cross. I have no idea. On a Wi-Fi network, how does a computer get an internetworking IP address, DHCP. What is network address translation? It looks up the, okay, no, it says it reuses special network numbers. How are IP addresses and network numbers managed globally? There are 5, blah, 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 yes. How much larger are IP6 addresses? I mean, if we talk about bits, it was 32 and 128, I think, right? So, or wait, so it was 4, but it was actually 8. I have no idea. If we're talking about bits, then it's let's do 50%. What does it mean when you come to receive an internet that started 169? It means you're on LAN, right? That's the LAN network. There was no gateway available. If you were starting an internet in Poland, would assign you RIPE NCC. Okay, how many physical links does a packet cross from its source? That's the question, right? Like, what do you mean physical links? It doesn't make sense. This question doesn't make sense. I'm gonna put 1 because the first one, but probably not good enough. Okay. Yeah. Yeah. Wow. Okay. Oh shit. Yeah. This. Yeah. Oh shit. So let's do this one. They are about the same size, twice, 10 times. So let's go 10 times, and let's do the smallest number. And how many? So 15. Okay, so 15. You mean it's like a destination, physical links. It means, if you mean by the hops, I guess it means the hops. But not too bad, not too bad. So that's it. That was our first very long stream of introduction to networking. I think we did super well in general. That's, I mean, of course, new information is this two chapter, but at least I take the time, and you can see it on the tests that like it makes most of the questions make sense. I just really like, my biggest fear is that when you know, when I need to apply this, or when I have to, let's say, impress someone with my knowledge, then I will just have the brain fart. So this is maybe something we can also talk about. This is very important. Fear of brain fart in critical moments. Yeah, so yeah, time to get my food. I need to get my food, to be honest. That would be nice. And now after that we're gonna go to the transport layer. Yeah, I'm pretty sure this will be done tomorrow. Yeah, this is a very short book, so it should be done. I still don't know if I should go tomorrow to the badminton thingy, because it's gonna have, but I think I should have at least some, like, there is time for that, for 1 hour. Like, if tomorrow if we start earlier, not like this, then it's gonna be, I think it's gonna be good enough. So